Brought to you by MuleSoft, provider of the industry-leading AnyPoint platform for APIs.
Okay, hello everyone. I'm going to do two slightly risky things here. One is I'm going to do a bit of live coding through this talk, so forgive me if things go wrong. And I'm also going to talk at an API conference, and half my talk is not going to be about APIs. I hope it'll make sense by the end, but bear with me if it seems like I'm completely off topic. So I'm from Wolfram Research, and what I want to do is talk about our approach to software development and some of the philosophies that we've built technology around, and hopefully show how that relates to APIs by slide 7 or so. I think I get onto that. So if you have heard of Wolfram Research, you've probably heard of us for one of two things. First of all, you might have used our product Mathematica at university when you were being forced to study calculus or something, and you were doing it, using it to solve maths problems and cheat on your homework, and you would type in things like this and get fancy maths answers out. And then more recently, we created this knowledge engine that's, for example, the knowledge base behind a lot of Siri queries, and you can ask all kinds of funky questions of it, like I could say, what are the flights over Chicago right now? And while it's thinking about that, let's do an even weirder one of something like weather in Rome when David Cameron was born. And hopefully we've got some answers coming back from those. So here's what you would see over Chicago right now if you look in the sky, and hopefully you can chain some weather information together and call the Rome weather station and get an answer on the other query. Here we go. So it was pretty mediocre. So my claim is that these things that we've been doing for the last 25 years, or some of it more recently, like computation, symbolic representation, symbolic maths like the calculus I just did, natural language, and semantic knowledge, the fact that I can connect different bits of information together, are actually relevant in developing APIs. And I want to go through sort of each of those in turn. So the first thing is computation. And the key thing about computation is that I would assert that computational knowledge is much more valuable than just the dead information. So if you think about the space of APIs, they tend to be either computational APIs that do something, that work something out, or a lot of them are simply database interactions. They either read information from a database or they change the state in a database. So a payment is in the end just changing a state in the database for how much you owe your credit card company and so on. But if you do something with that information, you can make it go a lot further. So let me jump back to Wolfram Alpha here and show an example of that. If I do something like, where is the International Space Station? Now, NASA provides an API that provides information on the location of the International Space Station, and we plugged into that API as a consumer and got some information out. But if I... Oh, don't time out on me. Give me the extra bit of information I want. Let me just do that one more time, because it decided not to tell me the key thing I wanted to point out, which is when NASA updated their API information. And it's not going to tell me. OK, so typically the NASA API updates about once every 2 hours, and it gives a snapshot of where it was at the last reference time. Now, the International Space Station goes around the Earth about every 2 hours. So the information, by the time you get it, is completely useless. And last time I looked at this, it was about an hour and a half old, so maybe it's just refreshed, which is why it isn't telling me. So it's using computation that actually makes the answer useful. Now, you could just say that's a bad API. NASA should just update you every 60 seconds or 30 seconds or real time or whatever, and then it would work. But as soon as you've got this idea that you can take that little snippet of information and make it go further, well, then you can start asking things like, where is this ISS in... I have 44 minutes, 53 seconds, let's call that 45 minutes time. And now the computation takes that tiny little snippet of information from NASA and gives me an infinite number of answers. So in 45 minutes, it's going to move and be over the top of somewhere near Australia. Now, if you think about all of these sort of most useful things in our lives, like sat-navs, the sat-nav would not have taken over from the Atlas if all it did was give you database lookup. Roadmap gives you the information. It's not the fact that the sat-nav could give you the information that made it useful. It wasn't even the GPS that said where you are on it, because most of the time you know where you are. What it really did was the computation. It was saying, given where you are and where you want to go, turn left. That's what killed the road atlas. It's the computation on top of the information that makes it go much further. So what are the key issues in adding computation to your base knowledge? Well, the bottom line is computation's quite hard. And even if you get your PhD mathematician in to do all kinds of clever computation on top of your data, it's hard for them too. And that translates into time and expensive personnel, and in the end, that all costs money. So what we've really, in essence, been doing for a long time now is trying to automate as much of the process of computation as possible to make it easy. And I'm not just talking about easy for somebody who doesn't know the maths, but it actually makes it more productive for even if you have got that PhD mathematician in to do fancy computation. So let's do some machine learning. I was watching something about the Titanic the other night, so this seemed like a good example. Here's a database of information. This is static data, hopefully. But one could have an API that was watching the mortality rate on all ships around the world in real time. And I could do a lookup from that and say, you know, what happened to passenger 42 and get some information out. But what if we wanted to make some kind of recommendation engine that said, passengers like you lived? Just like all of these sort of purchasing things that try and relate you to products, this is all a case of trying to match information and make predictions. And it's when you start making predictions from data that the data really starts becoming valuable. So what I need to do, what I'm talking about here, is effectively a machine learning problem. So what we try and do is elevate the computation you're doing to the highest level possible. So there's all kinds of algorithms for that. There's k-nearest neighbor and Bayesian methods and half a dozen others that I can't even remember the names of. But I don't care. What I want to do is I'm going to classify that data set, and we've already got a classification that we've got a type of passenger with the class they travel in, their age, their sex, and what happened to them. And I just want to say classify that. Now, really, in the small print here, is the key thing here is it says method naive Bayes. It's done that for me. So there's something about this data set. Maybe it's because it's a mixture of numeric and textual data. Maybe it's because it's only got a small number of classes. I don't know. I don't care. The automation is not just to run the algorithm that I've written or chosen. It's also automation to help me choose it. Now, I might be an expert on, I'm not an expert on machine learning, so I don't know the difference between when I would use Bayesian or random foresting is another method. I don't even know what the difference is. Even if I did, though, the chance that I would know all about that in great detail and all about simulation and all about classical statistics and all about graph theory and all of the things that I might need in order to do clever computation on your data is pretty slim. So automate, automate, automate all the way through. And having done that, I can now use this thing straight away. I can say, this is the classifier I've just built, and I'll give it some information it hasn't seen before, and it'll give me a prediction. And I guess we could make it a little bit more personal, since I'm not obviously 18 and a quarter. Obviously, I would travel in first class. I wish. And I would still die. So we have to multiply up this automation everywhere, but this is a sort of central philosophy that computers are about automation, but they're not just about automating the boring steps, they're about automating intelligence as well. Now, a key thing about computation as well is being able to interact with it. Now, of course, we'll talk about APIs later, where computers interact with it, but in the development process and in the testing process and in the marketing process, then you need to be able to work with the API without having to sit down and write a whole bunch of scripting code and some XML in order to feed it some complicated blob of structured data. And the same thing, the same kind of principles apply here as well, that we can take this thing we just built, this classifier. I've saved myself some typing here. I'm giving a couple of extra parameters here. I actually want to say the probability that I died rather than simply just the fact. So here it's making a prediction. And I want to start playing with that. So automation, again, is just part of that. I want to be able to say, well, let's have an interface to let me interact with that. And I'll have something I can control here, which is the sex. And it's going to have a choice of male and female and maybe unknown as well. Well, it doesn't matter. Unknown's not actually in the data. It's just a token that doesn't exist. I'll leave it as that. And I've got to close that bracket. There we go. There we go. I've got an interface. And I can now start saying, well, what happens if I went through the different cases? And I haven't used that parameter, so that would help. That's now the parameter. Now the probability changes as we go through which sex I am. And maybe this thing actually is not much use as a number. Maybe what I really need to see is a picture. So maybe I'm going to make that a parameter as well and make this a plot of that. And we'll have age going from 0 to 100. There we go, that's a bit more like it. So now I can see the profile of survivability according to what sex I am. So what's actually coming here is a combination of automation and symbolic computation again, because what I've got is, this isn't, it's a program, but it's barely a program. What it really is a symbolic representation of an interface, which is then being rendered by my computer using some kind of rules for how that should be displayed. It's sort of the bare essence of a program. Now, another key thing is integration. I said that there's all kinds of different computations out there. We need to make sure that not only do we have access to a big sack of tools that we can decide which tool is right for the job, but we need to be able to mix them together. And the tool set's got to be quite large, because the sort of space of things that you can do in data science and other kinds of computation is pretty broad, and there is overlap constantly between them. That we've got things like statistics and machine learning that we've just seen, but there's modeling and simulation like solving differential equations or time series prediction, and the signal processing things like filtering sounds and pictures. And these are all, boiled down to a set of routines, but what you need to be able to do is to mix them. Because what if your data happens to contain a combination of pictures and social relationships and numerical data, and you want to do something on all of those? How do you mix all that data type? Well, let me give you a crazy example here, which is not the kind of API I can imagine you building. I've created a bit of code here for solving mazes. This is a Blenheim Palace just around the corner from our office. And I've got here, I wasn't going to do this one live, there's about 20 lines of code. And let me just run through this quickly, because the solution to this maze isn't really the point of my code here. What I'm going to do is turn that into a black and white image and cut out all of the small blobs and noise. I'm going to thin those lines. I'm going to prune all the dead ends that don't go anywhere. That takes a few seconds. I'm going to get out some key information about the start and end points and just crop the bottom. And now I'm going to find every pixel that touches another pixel that's white. And I'm going to describe that as a graph of relationships about whether pixels are joined or not. And that gives me a nice topological version of the map. So here, hopefully in a second, is what it would look like as a London Underground version of the map. And then I can apply some graph theory, like finding the shortest tour, and then turn that back into an image and overlay it. And here's my solution. If you ever go there, don't follow this solution, because the trouble with image processing is it can't see this as a bridge. So my solution involves a bit of climbing and abseiling. But the key point of this example is not that I can do fancy computation. It's that here I've done very different types of computation. I've done image processing. I've done graph theory. I've done some linear algebra hidden in the middle. I might go on and do some geometric computations on here. So here's a plot of the distance from the exit or the angle that you were facing at any one time as you traverse the maze. And I'm dotting around different types of computation, but they all fit together. You didn't see any lines of code here that say convert this to that type or transform some object into something else. I can just kind of join the bits up. And the way that's done is by symbolic representation. I promise it will relate to APIs in a minute. So if I go back to where I started, we do fancy maths. Well, here's some very elementary maths. I'm going to change variables. You probably did this in school, and it's probably very tedious. I've transformed a symbolic expression from one to another. It's sort of classic computer algebra type problem. But while here it's maths, behind the scenes, this actually that's not what it looked like. I've changed my example. Put that one in. You'll see there's this sort of symbolic representation of what the maths looks like, that it's a function called plus, and it's got another function in it called power. Now, it happens to be that we know rules for these. We know that 1 + 1 is 2. We know things that plus does. But the operation that said do some substitution knows nothing of that, and it doesn't care. It's an abstract thing that says take a blob of symbolic data and turn it into another blob of symbolic data. And what that means is once you've got a language that can do that on maths, you can do it on anything. I can take something that's not at all like a bit of maths. So here's a laser scan of my face. I always have trouble with the orientation here. No, I'm facing that way. There we go. And it doesn't look at all like a school polynomial problem. But I can do exactly the same thing that say replace something in that symbolic object with something else, and I'll take all those polygons out and turn them into lines, and now I've got a wireframe version. I didn't need some language for transforming graphics. And you can now see through it, so all I've got is the edges now. And so if you think in this space that's out there, there's things like XML that you might pass up in some complicated API. XML is just a symbolic representation of whatever the markup language is. HTML is just a symbolic representation of documents. So once you've got a programming language that handles symbols, not bound into is it a number or a string, but actual structured symbols, you've got a language that can transform HTML or transform financial product markup language or any other sort of symbolic representation. And it turns out to be a really powerful idea that, as you've seen already, things like maths can be represented, but things like pictures, these can have a symbolic representation in terms of their primitives in vector graphics. Sounds in terms of structures like channels and lists. Things like social networks. A graph is simply another symbolic object where we've got vertices and edges. And likewise, images, well, they're fairly straightforward, but documents are a little bit more complicated because there's all kinds of things you can do. But even things like programs, the program itself is already in the symbolic representation. And things like NoSQL databases or tabular data, these can all be represented as things like key-value pairs in a symbolic representation. And even this interface that I'm clicking around here, this interface has itself a symbolic representation. It's a tab view of what's on the tabs and so on. So it's a really powerful idea. And it's what allows us to join up all of the different bits of maths into one system. But the core idea behind it is that all data is the same, if you think about this stuff symbolically. So when you're tapping into some database of pictures or some database of, as I say, social networks, if you're getting Facebook data out, all of this stuff is the same. You don't need to think, how do I get this into a matrix of numbers? There's no, you can just think about things in the abstract sense. So that means that this function I used before that said classify something, it doesn't have to just be a nice grid of text and numbers as I used on before. Here I'm going to, these are a bit small, let me make this the actual size. Here I'm giving it a bunch of photographs that are classified as night or day pictures, and it can classify those in exactly the same way. It's used a different method here. The automation kicks in, say, logistic regression's better. But now I can take a bunch of pictures it hasn't seen, and it tries to figure out whether they're day and night. From the machine learning that it's done, it's presumably figured out that the color palette's probably the most significant thing to decide, rather than the kind of shape of the contents. And likewise, other kinds of data that are completely different, like sounds. Actually, I think I already ran this piece of code because it takes about 10 seconds. I'm just calling exactly the same function. I'm saying, here's a bunch of sampled sounds, and they're classified as being wind instruments or non-wind. So here I've got, I don't know what that is, but if I ask it, it says it's a wind instrument, and this one, that I can recognize as a piano, and it will say a non-wind instrument. And if I prove that it really does not care, let's do la. You can tell why I'm not a musician. I'm a computer scientist. If I do that, it says non-wind instruments. That's probably fair. So stop trying to think of how you kind of coerce or pull out data of one type. You can handle all kinds of different things in exactly the same way once you think this way. Okay, dotting through these things I said we did, and I haven't quite shown the relevance there, but I hopefully shown the relevance in Symbolic why it's important to really be able to make the computation which will make your data or source information more valuable, and how that makes it easier. I'll come back to it. She has a direct relevance to APIs in another slide's time. So I also showed you this sort of fancy party trick of typing in phrases like, what was the weather when somebody was born kind of thing. And that's all about turning natural language into a symbolic representation that you can compute on. So that's got several benefits that are slightly more directly connectable to APIs. One is having a much more flexible interpretation. So you've got to start thinking about your audience here, who has to tap into your API. Now, they're supposed to be good programmers. They're supposed to read your pages of documentation on exactly how to structure a JSON request or exactly what the parameters should be in the XML that you're expecting from them, and they're supposed to follow that stuff. Well, they're lazy and they're careless, just like everyone else. And so one of the things that linguistics can do is to make much more fault-tolerant accesses to the interpretations of the information that they call your API with. So supposing we've got some field which is expected to be a number. I can interpret that I've got various different interpreters, but I'm going to use one of the loosest here, which is semantic number, which says, on the one hand, it's a restriction. It's saying it's going to be a number, but it's saying, just try and figure it out. So, easy start. 1.2 has an interpretation of 1.2. It's a number. That was pretty easy. And if I give it something that that doesn't look like a number, we get the correct failure. But what if I gave it something that was, to me, as a lazy programmer, a number, but might not be to you, let's say 1e20. Well, that's 10 to the power 20 in a lot of notations. Or if I use something like 10 star star, let's say I'm still using Fortran, that's 1,000 in Fortran notation. Or what if the thing has come from a user, and the user has typed in some field, and it's some granny who has no idea how computers like to work, and she has typed in 75. We can interpret that as well. So we've now got a field that has to be a number, but it's really loose about what that means to be a number. Likewise with dates. There's horrible ambiguity problems with dates, whether you're European or US. But to some extent, you can automatically deal with that. Hello. Taking a little time to think. Oh, come on. That should be instant. OK, it's finally thought that that's 31st of January. But so, arguably, is this. We know it can't be what have I done here? I've typed US format date. We know it can't be European because there were only 12 months, and so we can automatically interpret that by saying this must be US format. Obviously, you've got an ambiguity problem if I've got 1/2, that could be 1st of February or 2nd of January. But where it can be disambiguated, then we can be really fault tolerant. And again, maybe what we've got here is it's a delivery date, and our granny's at it again, and she says 3 weeks after Easter. Well, that's still a date, and with a little bit of thought, and it's interpreted as Easter this year, it's figured out that 3 weeks after Easter was this date. So maybe actually what I need to say here is 3 weeks after next Easter if it's a delivery date, and that's 3 weeks after the coming Easter. So there's all kinds of cool things we can do on your API that say whatever junk gets thrown into it, try and do something sensible with it. Now, of course, we don't always want to be as flexible as possible. You can be totally precise and say it has to be a string that contains only digit characters that don't have a decimal point. You can do all of that kind of stuff. But we can also restrict down and still keep that kind of interpretation. So we can do things like interpret a string in a completely different way and say this has to be a city. And the tooltip shows me it's found a little bit more information and decided that this is probably London, Greater London, United Kingdom, rather than London, Ontario, Canada, because it has to try and disambiguate, and it decides which is the most important if I haven't said Canada in here. And I can obviously reject things that it decides aren't cities, but at the same time, we have the kind of fault tolerance here. So if I say the Big Apple, then you can say, oh, well, that's just a synonym for New York City. And likewise, you can put sort of much more detailed pattern restrictions. I can say, OK, my number has to be from 0 to 100, and in which case it's going to reject this -5. So we don't have to, and I can, here I've not used semantic number, I've used number, which is going to rule out all of those fancy granny type entries. So another key thing here that is about making data go further in an easier way is about the semantic knowledge. And in fact, we're seeing a little bit of that coming up already here, that what came back is something we call an entity. It's not a string that contains the words New York City. It is a thing that represents a city. And what we tried to do is to build, and we're still working very hard on, an ontology that allows you to relate information together. So supposing we've got some information that the person wants to ship to New York City, well, there's all kinds of properties for that entity. Let's do some interrogation here, properties that are available. So it knows the relationship that cities have regions, and they have airport codes and freeways and all kinds. I might not have the information on this, but it knows this sort of ontological structure. So for example, I could say that every city lives in a country. And I give it that parameter, and what we get is back now a new entity, which is the United States. And the United States, countries have all kinds of properties as well. So I could say, what is the flag of the country of New York City? And we'll hopefully get, do we know, sure we know the flag of the US? So, or we could say, what's the, is it going to be called GDP, or am I going to have to look this up? Okay, so we've got a GDP here in terms of US dollars that we've looked up from it. So we can start taking information that is in one silo and joining it to others. This is how my David Cameron example works, is that David Cameron, it recognizes as a person entity. People have attributes like dates of birth and dates of death if they are not still alive and things like that. It knows that weather queries can take properties related to location and date and the attribute you're after, like is it raining or is it hot and so on. And it can join these up by figuring out where the intersections are between the data sets. And sort of much more little practical things like, we've got units here like, well, let's just type something in just directly in units. If I had something like $200, I'm just using a quick lookup here to turn that into an entity, plus another thing which is 200 pounds. Well, it knows all about units like, there we go. And so it knows things like the relationship between meters and miles and all of that kind of stuff. And here it's had to do a real-time lookup to say, well, what is a common currency and what's the conversion rate to make that work? So all of this kind of stuff you could program low level, but having a language that knows about the world and knows about relationships makes joining up your data with external data, meshing to APIs that come in different units, all just much more seamless. And so all of these things bring to bear just to reduce the development time and the development cost in the API you're going to create. Finally, I'm going to talk about some APIs. So let's say we took this program that I wrote right at the beginning. We want to make an API out of it. Well, it turns out symbolic representation can come back here again. I've pre-typed this here because it's quite a bit to type in, but I've got a representation here of an API function, and it's got some type information. This is the interpretation that we've just been going through, so the age I'm going to allow to be semantic, and it's going to call the function that I created right at the beginning of this talk. So what I get back, well, it's nothing. It's a symbolic object. It doesn't actually do anything. It's a representation of an API. And I've just named it API here. Oops. And so I can now test whether my API behaves correctly locally here on my computer. And so I can give it the information, and it's giving me the prediction as expected. And I'm happy this now is the kind of API I want to expose to the world. So I'll just take that object that represents the API, and I need to tell it permissions, otherwise you won't be able to use it. Goes to public. And hopefully, there we go. So I've just created this URL. It didn't exist a second ago. If you've got your laptop in front of you and you can type really fast, you can go and test this API right now, because I've just pushed this into our live production servers in the US. And because I just hand over this symbolic object and everything serializes beautifully when you have a symbolic representation, it can be interpreted that side, and instead of running it on, in this case, I'm running in a notebook environment in Mathematica, it's now going to push it into, instead of I'm on a Mac here, it'll be in a Linux-based cloud on a server that's serving up exposed web services. That's just a translation on the symbolic object. So if I go to this thing now and hopefully test it, so it's failed because I haven't given it the parameters I need, and so it's helpfully saving me typing in the question mark class equals. It's giving me a little interface here, so let's just give it some values here. And you can see I've been testing these kinds of things. So let's put in, I'm going to be 34 now, 35, and what sex? I'm going to be female now. And you can see this is the URL that I could have constructed in order to make that call, and it's returned a nice string ready to be interpreted on by whatever my client application is calling this from. So it's only through having the ability to serialize the entire program, the data set, regardless of what structure the data was, push that right over the link in this symbolic representation of an API. All of the stuff that I've done through this talk has been embedded inside this symbolic object, and it can just be delivered to the server and ready for live production. Now, it turns out that this kind of principle can apply to everything. If I go back here to, where was I? I was in interactivity. I made an interface here. So let's just grab that out and go back to where I am. Here we go. Right, so I created a testing tool for myself, but maybe I want this to be there for my users to figure out, well, what's my API likely to return, so that I can test whether or not I want to use it and see what the objects that come back are or the likely behavior. So let's call that interface. and we evaluate it. And now I should be able to do the same thing. I'll just say cloud deploy that interface, and permissions again goes to public. And internet willing, it'll serialize the symbolic representation of the interface, push that to the cloud where it's going to be rendered in completely different technology because we have to do it in HTML and JavaScript. And there's my interface that I've just created. And it works just like it did on the desktop, but it's now accessible to you with a browser. If you go there right now, you can use this thing that I've created. So you're starting to see the sort of workflow that we're trying to develop here for building APIs, that I can do all its fancy computation, prototype it on some static data, make a call into the actual live data, push the thing to a server, push interfaces for testing and marketing purposes, and the whole thing sort of live in the space of a talk. Still with 18 minutes left. I might even finish on time. And of course, the things that we've been seeing earlier all apply here as well. So maybe I won't even bother running with this one. I've got an API function where I'm using some of these restrictions that we talked about before. Let's run it and call that locally. And so it's the same as before, but now I've put a restriction on some of these things that says my string has to be first or second or third or unknown. So if I say my class was fourth, then we'll get a nice rejection on that. And if I push that to the cloud, I'll get the same behavior in the cloud. Okay, so output control is a kind of important thing for an API. I've done the simplest possible API here, where what I'm getting back is a string surrounded by quotes. Really easy to parse. But what if I actually wanted to send back some much more structured information? I need to start building up the kinds of parsable objects that are easily usable. So I've got here the same code as I had before. And this time I'm going to send back, well, actually, let me show you it in action. Another attribute of my classifier that I built is that I can list out all of the cases and their probability. So here's a much more structured piece of information where I've got a key value database being returned, albeit of just 2 values. So if I push that out to the cloud in its default, what we'll get back is Wolfram language representation, which is great if you're in the Wolfram language. But so let's just put some numbers in again. So here's the Wolfram language representation that we just saw right before us. Now, remember I said this is a symbolic object, and things like XML are symbolic objects. And when I started this, I did a fancy bit of maths where I took a symbolic bit of calculus, and I got an answer. What it was really doing is it was taking a symbolic representation of the question and transforming it into another symbolic representation of an answer. It's a transformation from one blob to another. That's all it's doing. Well, that's format changing. That's all that when you take a JPEG and turn it into a GIF, you're just simply transforming one kind of object into another kind of object, right, along with a bunch of rules. Computer scientists think of it as programming, but you can think of it simply as a kind of set of rules for transformation. And so that means that it becomes very easy to, if you can come up with the rules of how an SVG graphic relates to a PostScript graphic, that you can just create these mappings and transform them, just as I did my face earlier. So I can do this API here that I had before, and this time I'm going to return something in a different format, and all I have to do is give it as a format return type. Did that evaluate? Yes, it did. So now if I go to this one, you see that, well, my failure is now no longer coming back as an interface. It's coming back as a set of states in a JSON object. So now I'm actually going to have to type something here. It was age equals 44, and class equals first. And what was my other thing? Sex equals male. And so now here's my data coming back in a JSON object, which is going to be much easier to handle in other languages without having to write a parser. And if we want to, then some of these things we might return might be nothing to do with sort of structural things that, well, here's an example, a completely different thing I've written here, which says find the geopath from where it believes I am based on my IP address to a location, which I'm going to type in, and the location has to be a city. But what I'm going to return this time is a GIF. I don't want to see some kind of serialization of an object, so I can type in here, and let's do somewhere further away, let's do Perth, and call that API. And this time, our object isn't going to be a structured object, it's going to be an image in a GIF format. But maybe it is that I want a structured image back that has all of the kind of image goes to, and here's a serialization of it, and here's the states and the start and end and the distances or some other sort of structure that goes with it. There's a Perth in the UK. I was thinking of Perth, Australia. Never mind. Not so far. Okay, so I've talked mostly about how wonderful it is as a developer. I can write fancy computation, I can push it to the cloud, I can make my API tolerant and bring in external information easily. We've got to remember the consumer. And the consumer needs to be able to write the code to go with your API. And while we can make it tolerant if that's a good idea, then we also want to help them as well. So again, the symbolic representation of our API comes in useful here because that object holds everything about my API. It knows what was going into it, what restrictions were on the inputs, it knows what outputs are going to come back, it knows what URL it's on. It's got a whole bunch of information. And so I can now do exactly this kind of transforming one symbolic object into another to say, right, give me a Java program that matches the call to that API. So here's the Java program required. I can copy and paste this into Java, and it'll make a call to my API, and it's already set up with types and presumably some appropriate error handling. And if I put something else in like C++ Visual Studio, we'll get a completely different blob of code out. Oh yes, yeah, that's it done. A bit longer. And I guess if I'm using something more modern and high level, then, whoops, close my quotes. Then I'll get a much more compact piece of code. There we go, that's a little bit cleaner. So we're trying to think through these workflows that go not just for the developer workflow, but also the consumer workflow. Now, of course, if you're consuming from within the Wolfram language, then all of this stuff's fairly straightforward. This is our code for calling one of these, is just URL execute, and it knows all about the serialization of the fact that I'm giving here a number. Whoa, no. Sign and catch, I didn't make whatever URL that was public, so let's grab one of the ones I did earlier. What was this? This looked like a useful one. And let's put that into the URL. Don't want the cloud object bit. Yeah, there we go. So it's fairly straightforward because, again, having symbolic representations behind, serialization of everything is sort of automatic, even though here I've only got strings of numbers. If I sent something complicated like a graph over, that would need serializing appropriately. But we're never satisfied unless we can make things as easy as possible. So one thing that we're trying to add in on our language level for the Wolfram language consumers, people who are consuming APIs from within our environment, is to try and curate APIs in a very abstracted level. So again, what we're trying to do is to get rid of all of the details as much as possible and just have a kind of common interface to the main usages of APIs. Now, sometimes you need all of the details, but what we want to do is for the main cases deal with that automatically. So here's the sort of commonality is that I've got a service connect. In this case, I'm going to connect to Facebook, and all of the authentication's hidden. The first time I had to do this, I had to authenticate, but it's remembered me now, so I'm authenticated in, and then I've got a symbolic object representing this service, which I can then call. I'll say, execute on that, a friend network, and I'm then going to do some computation on it, which is just going to look for communities within my, my friend network. This is where you find out how unsocial I am, because you can see I don't have many friends. But it has successfully broken it into a group of family and friends, people who are ex-employees of my office, and people who I interact with in our US office. Seem to have formed 3 neat families. But the idea is that this is sort of a sort of minimal interface that then is common across lots of different APIs. So now if I go to something completely different as a service, I'll connect up to my Twitter account, where I'm even less social. So you can see if I query that by executing a user data request, you'll see I've got 4 friends and 20 followers. But then I can interact with all of the main features of this service. So I'm just going to grab here a picture. Nope, the camera didn't wake up in time. Let's do that again. Oh, that's a terrible picture. Let's put a smile and look at the camera, for goodness sake. There we go. So I've grabbed a picture. I can now service execute Twitter. I want to do an image tweet. And here's the text, and I'm going to send that image. And now if you go and I wouldn't recommend following me, because I don't say very much on Twitter. But hopefully in a moment, when that comes back with a response, there we go. It's now tweeted to my network, the picture that I just captured. So I mention this partly because at the moment, we're just at the beginning of this process of having the language know about the world of APIs, just like it knows about the world of socioeconomics and cities and countries and space stations and the like. And so if you have APIs that are, I think, generally useful to a computational community, I'd be happy to expose the internals of this function and absorb them into the Wolfram language themselves if they're at all in line with our sort of corporate interests. Don't know how to put that better. As long as they're a sensible API, we'd love to include more APIs just in the core language so that anyone writing in the Wolfram language can just say service execute your API and whatever the sort of top-level request of what you do and put the kind of thin glue of serialization over the top to make this as elegant as possible for the end user within our language. Of course, you can always call it at a URL level. So this is really just syntactic sugar, but you can never underestimate how much you need to make life easy for people for them to embrace and adopt. So we're always trying to figure out, can we just go one step further? Because it's maddening when you say, look how clever my stuff is. And the person goes, oh, square brackets in your programming language, I'll never get used to that. You can't underestimate the barriers of learning and using new technology. So far, this is an API conference. We're mostly talking about things in the cloud, web services, but there's a sort of hybridization that is only just emerging, which is the whole Internet of Things. Now, it's easy to think of the Internet of Things being about objects that can call your service, because objects are dumb. So they need your service to do something clever, like if I've got some scales and I want to say I've eaten a donut and 3 jam tarts, and it says you put on 3 pounds, how much running do I need to do to burn that off? That all is going to go off to your service in the cloud, do some computation, and your scales will just repeat it back to you. But devices are not getting so dumb now. That there's this new generation of embedding that is saying, let's forget this effort of making kind of 5-pence 8-bit chips and spending millions on coding to make the thing do anything with that chip. Let's just embed a whole computer. There's the Raspberry Pi is on the market now, full Linux computer for about £20. Intel's coming out with the Edison, a full computer in an SD card. And so the idea that your objects, physical objects in the world, can actually serve up APIs of their own is just as important as them calling out to APIs that if we want them to be able to talk to each other, then they need to have the code running on them in a serious way. And this is where linguistics also becomes quite important, because it's an emerging field, so there's no standards. If your scales want to say, how much did the person eat, how many calories did the person eat or whatever, and the fridge says eggs, they had 3 eggs, and another fridge answers back and it says they had an omelette. You've got to be able to deal with these things by being able to linguistically translate. So having fuzzy interfaces can be very important when you've got a wild west of devices talking to each other that will emerge over the coming years. So our answer is run the whole damn lot on the embedded system. So we do a bit of code generation, but it's not really a good solution. What we try and do is we're porting the whole Wolfram language, the whole environment that you've been seeing, onto these little mini computers. So if I take this classifier that I've just built, and that's somehow useful to have built into maybe into a life belt on a ship, where you put it on, it can tell you whether you're going to make it, then I can embed that whole machine learning framework and the API into my device, stick it in the life belt, and then all you need to do is put on a human interface so that the person can provide their information. And maybe that comes as you jump off the ship. It looks you up in the records to see what your booking information was and tells you your fortunes. So I hope that after getting through about 25 minutes, I did make some of this relevant to your world in terms of building, connecting, consuming APIs and adding more value into the services that you're providing over your APIs. My key points really in the end are, it's computation that makes the value, that makes that database of data tell you something new, predict the future, give you insight, tell you more than simply verbatim, here's the facts that are in the database. That this whole symbolic representation is in fact a key enabling technology that makes data, programs, API objects, interfaces, documents, the whole thing the same, so that you can operate across multiple types of data and multiple structures of data and have stuff just work without too much of getting half a dozen open source libraries and then spending the next 6 months trying to make them talk to each other. And if you do have an API, that you think would be interesting to our user base, to the Wolfram Alpha users, come and talk to me. Thank you very much. We've got 4 minutes and 19 seconds for some questions. Thanks.
Brought to you by MuleSoft, provider of the industry-leading AnyPoint platform for APIs.